Okay, in less than a week, you're going to have your midterm exam. And here's an outline of what I sent you in today's email. So at least half or more of the exam will be things taken, well, even more than that, things taken directly from assignments, quizzes, and labs. And the recent quizzes and assignments were by and large MOPs, so there will be quite a few MOPs, but there could be other types of problems that showed up in assignments and quizzes. The emphasis, however, will be on the last 2 weeks, especially when it comes to these last 3 items. So what's different in the midterm is you're going to be asked to do a lab exercise, and it will be something from L6 or L5 or L6. This was L5, the fan cart. This week we did the Brock and friction in the centripetal apparatus. That's L6. You will be asked to do one of these exercises, something similar to what, identical or similar to what you did in lab. There will also be a lab problem that you have to solve using the formatting that I discussed: diagram, free body diagram, sum of the forces, etc. I'll illustrate this later in the video. And the final thing that I didn't mention in lab, but did mention in email, is there'll be at least one essay question on a concept or a physical law. And when you do that, I'll prep you on this. You need to use words, equations, diagrams, and examples. So answering questions in physics, even an essay question, involves not just words. You need to include equations, diagrams, and examples. Remember, definitions of terms are often equations. Okay, so I don't think I'll spend too much time talking about this. You should review the labs and make sure you know how to use a stopwatch and measure a distance and a time and set up the track and read the angle indicator. All those things we did in lab, you will be expected to do, and you'll have to do it on your own. So just review that. Keep in mind, this will be an in-house lab, and if you're doing something, I will be present, and you can certainly ask me questions during the exam. So let me now show you, sort of in real time, how to solve a problem, a lab-related problem. Let me give you one and actually do that. Okay, here's a problem from Lab 5, Task 2. If you remember that, the cart flat on the track with a pulley and a string and a counterweight, a hanging weight. And let's just say it takes 11.5 grams with the fan set at 45 degrees to hold the cart stationary on the track. So see if you can solve that problem, showing all the work. Pause the video and see what you can do, and then come back and see what I do. Okay, so I know enough to, the first thing to do is to draw the diagram of the situation. So I show the cart, the rope, the pulley, the hanging mass. I didn't give you the information about this, but this was 300 grams. Oops, that's 11.5. I didn't write that correctly. And then I did step 2. I drew the free body diagram. And when you draw the free body diagram, all we care about is the fan force and the tension force. They're equal and opposite. We're not going to use these, but if you don't put them in there, the free body diagram technically is not correct. So you need to identify all the forces. So there's the force of gravity on the cart, which is the mass of the cart times g, and then there's the force of the track supporting the cart, pushing straight up. That's the normal force. So pause the video and continue with the next steps and go as far as you can, hopefully all the way to the end. So since it's a force problem, the next step is to write down Newton's second law. The sum of the forces equals the mass times the acceleration. Notice this is a vector equation. So in order to use it, I need to separate out the components. So I do that. You see that in all the problems. And I put the sum of the force x equals max. And the sum of the forces in the y direction equal may. So now these are the general equations we're going to use to solve the problem. Now we put in the specifics from our free body diagram into these equations. So in the x direction, we have the positive force Ft and the negative force in the negative direction, F fan. Actually, I neglected to put in the cosine of theta, right? The cosine of the fan angle. Because if the fan is pointing to the side, the force that's going to move the cart forward along the track is F cosine theta. So I should have had that over here as well. And that, of course, is equal to 0. And the sum of the forces in the y direction are going to be Fn minus Fg equals 0. But we don't need this in this particular problem, so I'm not going to write it. Anyway, this ends up being, if we solve it, F fan equals Ft divided by the cosine of the fan angle. But we have to find Ft, and you might say, well, we know what that is. Ft is just mg for the hanging mass. But you do, if you're showing all your work, you do need to do a free body diagram of the hanging mass with the Ft and the Fg, or m for the hanging mass times g. I'm not writing very well. And then if you write the sum of the forces in the y direction for this free body diagram, what do you get? You get Ft up minus m for the hanging mass, g down, and they're equal to 0. Why? Because if the cart's not moving, the mass isn't moving. And so that finishes the problem. We get Ft equals m of the hanging mass times g, and now we can substitute that in there, and we get our final solution. Got to label that hanging mass, not the mass of the cart, right? And that's equal to the cosine of the fan angle. And now the final step is to do the calculation. So I'm crowding everything in. It's getting a little messy, but the fan force, the M, is the 11.5 grams, so it has to go in as 0.0115 kilograms. The 9.8 meters per second squared. Notice I'm writing the units. If you don't write the units, I'll complain. And that's all divided by the cosine of theta. And so the final step will just be to process those numbers, and you're finished. And so when you finish that calculation, you end up getting that the fan force is 0.15940 or continuing more digits, and that's kilogram meters per second squared, or newtons, but of course that's too many digits. So the question is, if I give you 45 degrees and you rounded to 2, that's only 2 digits, you would round to 1.6 newtons. Or if the angle had been 45.0 degrees, then you could leave it as 0.159 newtons, remembering that the number of significant figures has to match the significant figures in the data that you're given. Let's look at Lab 6, Task 2. Remember, you tipped the track until the block would slide down at a constant speed. and you might have had to get different readings at different places on the track. So in this example, the mass of the cart is 152 grams, and the data that I got was 19.5 degrees on the top and 20 degrees in the middle and 19 degrees at the bottom of the track. And so we want to use that data to find the coefficient of friction. So let's do the general solution, and then we can calculate for what the coefficient of friction is. So remember the routine diagram, free body diagram, sum of the forces x and y. So do as much of it as you can, try and do the whole thing if you can, and then come back and watch me. I'll keep reminding you that you do as much as you can on your own. If you just watch me, when you go to do it, you won't be able to do it. So if you didn't try drawing the figure in the free body diagram, you should do as much as you can on your own. So the diagram is easy. It's just an inclined plane, and the only thing that's of importance, well, the mass of the cart. Actually, the mass of the cart isn't important, it turns out, but the block, the angle is important. There is one feature that you might overlook, and that's that we're going to call the line along the track the x-axis, and the line perpendicular, or the direction perpendicular to the track, the y-axis. So the free body diagram, as always, is a separate diagram. It's free of the diagram, and you only show the object. So I'm only showing the mass, and there are three forces acting, and check that you got it right. The Fg, gravity, the mg force, must be straight down, perfectly straight down. The Fn should not be pointing up. It needs to be pointing perpendicular to the track. So make sure you get that right. Remember, normal means perpendicular. That's why it's called a normal force. And friction is always parallel to the surface. And so I'm calling it script Fk, K for kinetic friction, or sometimes we write it as F fric. Now, since we've chosen this direction as y and this direction as x, the Fn and the friction force has no components, but the gravity force has a component along y and a component along x, and they make an angle of theta, the track angle, with this vector. So because this component of the force along the track is opposite this angle, it's mg sine theta because it's opposite. And the one that's parallel is mg cosine theta. And in the MOPS, since this is the part of gravity parallel to the track, the MOPS calls this F parallel. And because this is the component of gravity perpendicular to the track, the MOPS will call this F perpendicular. Just so you're used to the accustomed to the different notations. Okay, now we have the diagram, free body diagram. Write down some of the forces, separate the components, and see if you can do all the algebra to get to an answer for, what are we looking for? The coefficient of friction. That's the mu k. So see if you can do that part. So a couple more comments. So this is a vector equation, and Newton's second law says that the vector sum of all forces equals the mass of the object times its acceleration. So Newton's second law is a relationship between force, mass, and the motion of the object. But since it's a vector equation, we have to deal, just like projectile motion, we have to deal with the x and the y part separately. So I write down those general equations. And now I'm going to, what this is saying, this is like a statement, it says take the sum of all forces on the left side of the equation and set them equal to the mass times the acceleration on the right side of the equation for both directions. So go ahead, try and do that if you haven't already done it. Okay, let's see how you did. So the reason we have a free body diagram is so it guides us when we sum up the forces. So I go to my free body diagram and I see what are the forces in the x direction. And I see in the positive x direction there's mg sine theta. And in the negative x direction is the friction force. And because the block slides at a constant velocity, the acceleration is 0, and so the friction force has to be equal and opposite, equal in magnitude to the mg sine theta. And the friction force is mu k Fn by definition. And so the mu k is what I want, so I divide both sides by Fn, and I get this. But I know the m, I know the g, I know the theta, I don't know the Fn, so I get that over here. So we go over to the y part. When I look along y, what do I see? I see Fn going up. I see mg cosine theta along the negative y. And of course, in this direction, there's no acceleration, so that's 0. So Fn is equal to mg cosine theta. So now I can substitute this in here for Fn. And what do we get? We get mg sine theta over Fn mg cosine theta. And m over m is 1. G over g is 1. And there's the answer, but sine over cosine is tangent, so we can simplify this to tan theta. And out of all of that algebra comes a very simple solution, that the coefficient is the tan of theta. So if I go back to my data, I would average those three values, and I would get an average of 19.5 degrees. And so when I put 19.5 into my calculator and take the inverse tan, I will get the answer to 3 significant figures for the coefficient of kinetic friction. Okay, we'll do one more problem. Let's do Lab 6, Task 4, the centripetal motion apparatus. And so the data we got was I spin it 10 times and it takes 7.5 seconds. And the radius of the spinning is 20 centimeters. And the mass is 500 grams. So draw a diagram of the apparatus that captures what we're doing. Think about it, think about the important parts, and then draw a free body diagram of the object that we're going to study, and then come back. Or if you can keep going, then write down some of the forces and solve the problem for the spring force. What we're looking for is the spring force. So try that. Okay, here's the apparatus. There's the central axis, right? And then there was the piece across the top. And if you say, I can't do this from memory, well, the apparatus would be in the lab where you could copy it. So the axis, the top piece, remember there was a counterweight. That's not essential, but I'm putting it there. And then the mass hangs down from the rod on a string. And then the spring was attached to the center axis post and to the mass, and then there was a pointer. And notice the way I've drawn it, the string is straight up and down, the mass is directly over the pointer, and the spring is horizontal, right? So from the lab you know that we don't want components for any of these forces, and so they do need, the alignment is important. What I left out that should be in there is I should mark the radius r. And we measured the radius right from the pointer to the center of the pointer to the center of the axis, because when the thing is spinning you can't move it. And I might show the spinning something like an arrow like that. And so this is spinning, and so what I'm doing is I'm taking a photograph when the mass is at this position because it's going around, and then I'm showing the diagram that way. And according to this diagram, the free body diagram has three forces. It has the tension force, which is straight up. I should make that even straighter up. There's the force of gravity on the mass, mg, which is straight down, and then the spring force, because of the way I align the spring, is perfectly horizontal. And don't make the mistake of putting a force in this direction. There's no force in that direction, right? At this instant in the photograph, that mass is coming towards us. It's coming straight towards us, and it's being pulled around in a circle by the spring. So the spring is the centripetal force. Okay, now we want to solve for the spring force, and let's do that. So you know the routine. We write down the vector equation for sum of the forces equals mass times acceleration, and we separate out the components. If we look at the y components, there's no acceleration, and so there's ft up and fg down, and they have to be equal and opposite. We don't actually need this for this problem, but I wrote it down. If you didn't write this, it would be fine. But we do need this because we want to get the spring force, and the spring force is, surprisingly or not, the only force in the x direction. So it's equal to the mass times the acceleration, and this is not zero, clearly. But that's a mistake you could make. So it's the mass times the acceleration, and the acceleration of an object moving in a circle at a constant speed is found by getting by squaring the velocity, or the magnitude of the velocity, divided by the radius. And so what we have up here is we have the radius in centimeters. We'll need to convert it, but we need to use the radius and this to get the velocity. So see if we can get the velocity and the acceleration and the mass and the final answer. See if we can finish it now. Okay, it got a little crowded, so we get the v by taking the circumference of a circle, the distance it travels in one rotation, and the time of one rotation. That's 10. So that's 2 pi times the radius for the circumference, but that's 0.2 meters. The point isn't there. Divided by 0.75 seconds, and it came out to be 1.2566 and some digits meters per second. So then that comes over here into the v. I square it. I divide it by the radius, 0.2 meters, and I got this number, 7.89896 something. That's the acceleration. But I don't really need to keep that. I just multiply that by 0.5 kilograms, and then I get 3.9478, etc. newtons. That would end up being reported as, three significant figures for this, 3.95 newtons. So there's the full-blown solution. Okay, the last thing that will be on the midterm and the final exam that you're not accustomed to is writing essay questions. And so in the email I gave you 4 different possible topics to write about. One was define and distinguish between average and instantaneous velocity. Second, explain Newton's third law of motion. Explain the concept of friction, static and kinetic, and explain what the terms centripetal force and centripetal acceleration refer to. And you're always, in answering these questions, you're always prompted to use words, equations, diagrams, and examples. So whenever you answer, make sure that you're including all 4 of those. So let's start with number one. Why don't you try that? Jot out some notes. You don't have to write it out, but think about how you would write an essay question, several sentences on the difference, the definition and the distinction between average and instantaneous velocity, using words, equations, diagrams, and examples. The first thing to note is that in physics, equations are definitions. So this is the definition of average velocity. It's on your equation sheet. The average velocity is the distance, the displacement, and I should actually make that clear. It's not a distance, it's a displacement. It's actually x final minus x initial over the time change. That is the definition of average velocity. It is not the average of the two velocities, although that equation can be used sometimes in special cases where you take v final plus v initial over 2. That works in a limited number of cases. This is the definition, and this is the definition of instantaneous velocity. It is the limit as delta t goes to 0, if I just read the equation from the equation sheet, of the change in position over the change in time. And as the time interval goes to 0, this ratio of delta x delta t becomes dx dt. So the instantaneous velocity is the derivative of the displacement with respect to time. So the first thing you should do if you're answering this question is write down these two equations and then put some words into them, like I just did, right? And now you want a diagram and an example. Well, I don't know how much a diagram is going to help here, but an example would be if I travel from my home to school, my average velocity, say I do 30 miles in 1 hour, equals 30 miles an hour. It's kind of a simple example. Obviously, the average velocity, the instantaneous velocity, which is what the speedometer reads at any instant, is going to be quite different at every instant during that time. Or use an example for lab. When the cart goes down the track, it starts at a velocity of 0. It has an average velocity, say, of 40 centimeters per second. And when it reaches the bottom of the track, the velocity is 80 centimeters per second because it's changing. And so there's an example from lab where we can distinguish the average velocity is 40, but between the beginning and the end, the speedometer reads every number from 0 to 80, and so it only passes through 40 at one instant. So there's an example, a couple of examples that you could use to illustrate the difference between average and instantaneous. Another useful insight into the idea of velocity is that any velocity is a distance over a time. And in order to get the velocity at a certain point in space or time, you need to take the average velocity over a very short interval. And as the interval approaches 0, that's the whole idea of calculus derivative. As the interval approaches 0, the ratio approaches a limiting value, which is the exact instantaneous velocity at that moment. When we come to Newton's third law, there's no equation, but we know that is the action-reaction. And the way I like to put it, and I've talked about this in the videos, is that forces arise from interactions. So if I'm on a skateboard and you're on a skateboard, and I push on you, here's a diagram, right, explaining it. I push on you, then you go that way, and I go this way. And that force of me pushing on you is the same force of you pushing on me. And because I do the pushing, you don't think of it, but it doesn't really matter who pushes. That force is always equal and opposite. So if I draw the free body, the force on me resulting from the push, the force on you has to be equal and opposite. And we don't tend to think that way because, we think like, oh, I push harder on you. It doesn't matter how hard I push on you. If you're heavier than me, more massive than me, I'm going to go this way at a higher acceleration than you do because the forces are equal and opposite if the masses aren't equal and opposite, right? A small mass will mean a big acceleration, a big mass will mean a small acceleration. And so you can give many examples of a tennis ball hitting a tennis racket, a ball bouncing off of a wall, a car pushing off on the road. If you're on sand, right, the car goes this way and the sand goes that way. So there are many examples you could give of that action-reaction. The important thing is that the force of the interaction acts on two objects, and that force acting on the two objects is always equal and opposite. So there's a lot of video material in these last two topics, but if you had friction, you would start with the equations, the definition of static friction is less than or equal to the coefficient of static friction times the normal force. And similarly for kinetic friction, except it's equal in that case. And you might try explaining why one is equal and one is less than or equal. I talked about that. So you start with this and you point out that the force of friction depends on two things: the coefficient, which is kind of the stickiness of the surfaces, and the normal force, which is how hard the surfaces are pushed together, right? So if you have a block on a surface and you want to pull it, there'll be an opposing friction force. And if you apply just, well, here's a good example of this less than or equal to. Let me erase this. So a crate is sitting on the ground, nothing's happening. Let's say a crate on a concrete floor. There'll be only two forces acting: force of gravity and the normal force as it sits there. Now, if I attach a rope and I pull this way with a small force, it won't move because friction holds it. So that means the static friction is exactly matching my force and it doesn't move. And if I pull a little harder, still not pulling too hard, it still doesn't move. So that means the friction force got bigger, right? The friction force isn't just acting until I pull. Now at some point the force will get big enough where the friction force can't get that big. So that's the equal to. There is a limit to how big the friction force is, and that will depend on the coefficient, how sticky the two surfaces are, how rough they are, and the normal force. So let's just say it takes 100 newtons to get this box started. That's the limit of this force. But if now I add some weight to the crate, then this gets bigger, and the normal force gets bigger, and the two surfaces are pressed more tightly together. And if I double the normal force, now it will take 200 newtons of force to move the box. In the case of static friction, since it's sliding, kinetic friction, since it's sliding, there's just the one force, because kinetic friction doesn't begin acting until it's already sliding. But again, there's the two factors that determine the coefficient and the normal force. And so there's equations, a lot of words, and diagrams and examples explaining friction. Also, it's a good idea to use examples from the lab, right? So if you go to centripetal force and you want examples, you might as well use examples that we did in lab, and other real-world examples like from the MOPS, like swinging a bucket of water, or a car going around a circular track, or the amusement park ride. So there's a lot of diagrams, examples, and explanations in the first 15 minutes of the centripetal force video. And there's a lot of information about centripetal force and acceleration in the Lab 6 questions, so you should study that. But obviously, the centripetal force leads to an object moving in a circle at a constant speed. The velocity, the acceleration vector is always perpendicular to the velocity vector and parallel to the force vector. So you should draw diagrams like this. And because the force is perpendicular to the velocity, it doesn't change the speed. It only changes the direction. And to calculate the centripetal acceleration, you should of course mention that it's the speed, which is constant, squared, the magnitude of velocity squared, divided by the radius of the circle. And again, use examples from the MOPS or from the lab to explain and illustrate those concepts.